In this lesson, we'll introduce the concept of structured representations. That is, unlike convolutional neural networks, which have very specific connectivity biases, we'll try to develop architectures that can learn some of these structured representations explicitly. Thus far, we've talked about how to build and optimize deep feed-forward architectures consisting of linear and nonlinear units. And again, this can be generalized to arbitrary computation graphs. And we can use backpropagation and automatic differentiation to optimize them. We've talked about convolutional neural networks, which alternate convolution, pooling, and nonlinear layers, as well as fully connected layers at the end, in order to process spatially structured information, such as images. One of the main motivations for convolution layers was adding architectural bias in order to represent the things that we know are true in images, such as stationarity, that is, small local features that can appear anywhere in the image. And we showed that indeed it is able to learn, after optimization, a compositional feature space. That is, low-level features such as edges or textures or color, mid-level features representing shapes such as circles or corners and so on, and then object part. If you think about it, what we did in convolution layers is to add this architectural bias and specifically determine how the connectivity between nodes and receptive fields in the image interact. But we may want to do this in a much richer way. For example, we may want to represent arbitrary items or elements, not just pixels, let's say also words or other items in the world, and try to model how relationships between them exist, and try to do that in a learnable way. And this is true because compositionality exists not just in computer vision. We also have it in other domains. For example, in speech, we have things like different input representations of the raw audio, as well as phonemes and entire words and sentences. And similarly, in natural language processing, where we have text, we want to represent the compositional nature of language. And so we may want to think about designing general architectures that can explicitly learn to represent these kinds of compositional elements in a way that's not as strong in terms of architectural bias. That is, we don't, for each modality or domain, explicitly try to design the connectivity structure to represent the compositional nature in that particular domain. But we may want a more general mechanism that can automatically learn this compositional structure automatically. And the structures that we want to model, that is, the relationships between different elements, may be even higher level than each different modality. For example, we may want to model the relationship between different elements in a scene, such as shown here. This is what's called a scene graph. We want a graph representation where each node can be an object or an object part, and we want to model the spatial or other types of relationships between them. In this case, showing that the man is wearing a hat and that the mountain is behind the horse. And this similarly occurs in language, where we may want to model more than just the sequential structure in a particular sentence. We may want to model different interrelationships between the words. For example, being able to model which words come across which contexts, or being able to model things like parse trees or grammatical structures. And the structures that we want to represent may go even higher level than that. We may want to represent all concepts in the world. This shows a dataset called Wikidata, which has elements such as people and places and occupations and so on, and maybe even has information about relationships, such as a person can be an author. And we may want to learn feature vector representations for each nodes in this. For example, each element here, each data point, might want to have an associated feature vector representation. And this feature vector should represent the structure in some way. For example, things that are conceptually similar should also be similar or close by in terms of their feature vectors. And we can maybe even also explicitly represent this as a graph. That is, we can have nodes and edges, where edges represent some sorts of relationships or similarity. If you think about it, the current architectures we've discussed, fully connected layers and convolutional neural networks, can't really represent these kinds of structures. In some sense, convolution layers do add architectural biases in terms of connectivities. That is, based on our knowledge of computer vision, we add some bias in terms of how nodes are connected to the image. But what we want is something more general. That is a general method to represent relationships between different items. And we want to do this in a learnable way. That is, we don't want to impose connectivity patterns for particular domains. We want to just have some representation that can hopefully learn this connectivity pattern given the particular data and the structure in it. And so we'll talk about various forms of architectural biases that researchers have developed, ranging from recurrent neural networks, which are typically designed for things like sequential data, to more general attention-based mechanisms that can up or down weight a whole range of elements in a set. And this can be an ordered set, such as language, or it can be an arbitrary set of different unordered items. And we can then generalize this even further to a graph representation where we explicitly model nodes in this graph and their feature vectors and then represent the neighborhood of that node. And we're able to use that structure to refine the features to represent not just local features, but also features of the neighborhood. And so really graphs are the more general way to look at this. We can have embeddings or vectors for each node. And we'll show how to do this. We already know how to do this for images. For example, we can feed it through a convolutional neural network, for example, that's pre-trained. We'll show how to do this for things like words. But we can, in general, come up with embeddings or vector representations for anything. And then once we have these embeddings, we can represent them as a graph where the nodes are feature vectors and the edges represent some sort of connectivity or similarity typically. And so for each node, for example, C, we can find the input nodes, that is, nodes that are similar in terms of some type of relationship. And this can be multiple types of edges. For example, we can represent in that computer vision image example something being on top of the horse or something being in front of or behind. And these can be different types of edges. When representing structured information, such as graphs, there are several things that are important. For example, we'll have what's called a state or vector representation that compactly represents all the data we've looked at thus far. In the beginning, this is just the different nodes or elements that occur in this image, for example. For example, the mountain, the man, the horse, and so on can all have features associated with them as extracted from a convolutional neural network and an object detector. So each of these regions of interest have associated features to them. We then have things like neighborhoods, which represent what other elements to incorporate. These are the edges in the graph. For example, should a man and a horse be connected for this image? And if so, through what relationship? Typically, we do things like similarity relationships, although in this case, you can also see other things like spatial relationships or verbs that one element is performing on the other. And then once we have the nodes and the relationships, that is the edges, we can propagate information. Now, what we want to do, for example, is represent as a vector the notion that the man is riding a horse. It's not just any man, it's not just a horse independently. These are two interconnected objects. And so we may want to have a representation, a vector that represents that relationship. And so what we'll do is through the nodes and the edges, perform some functions or computations in the computation graph that combines these different vectors together in a special way that we'll see, for example, a weighted summation in order to come up with a new vector that represents not just the individual items, but also the items as seen through their relationships. This is essentially a problem of propagating information. And again, after this propagation of information, you get a new state or new vector. Now I'm showing a visual example right now. Similarly, in language, you'll have a set of words that will read through the document, and we'll have a state representation that will track through the sentence. And in that case, it's not a complex graph structure, it's just a flat, linear, sequential structure, but concepts that we'll learn actually will relate to all of these different types of forms of structures. One of the key elements for how to update the representation of a particular node based on its neighborhood or some other sets of elements is what's called an attention mechanism. And since we want to have a differentiable attention mechanism, typically we'll use things like softmax functions. Specifically, given a set of other vectors that we want to weight up and down based on the current node that we're representing, we'll essentially do a dot product between our current node and all the other nodes, and then have a softmax function on top of that to convert it to a probability distribution. In that way, you're weighting all the nodes, and then we'll actually compute a weighted summation of all the other nodes and use that to refine this particular node's representation. This notion of attention is extremely powerful because it allows you to represent some arbitrarily sets of information. And this set can be any sized. You can apply the softmax function to any sized set, and you can then automatically use that to weight and combine information. And so again, this can be applied to all manner of structures. This can be applied to sequential structures where as you're reading a sentence, for example, to translate it to a different language, you can essentially look at arbitrary past words and weight them up and down every time you're converting it to a new word in the target language. Similarly, you can apply this to graph structures such that every time you process a node, you can find the weighting or similarity to all its neighbors and use that to do a k-nearest neighbor type refinement, except in a fully learnable way. Now, we've talked pretty generally about structured representations and relationships between different items. And so we'll make this much more concrete as we move forward, and we'll talk about specific structures, specific representations, and specific applications, such as natural language processing. However, let's start with a simple example that relates nicely to convolution layers that you know about. If you remember, convolution layers were developed because it did not make sense to connect an output pixel to all input pixels across a high-dimensional image or feature map. This is because we know that we'll probably want to extract local features, edges, and so on, and that doesn't require tying it to the entire set of pixels. However, we can actually generalize this and allow the network to learn its own connectivity pattern through an attention-like mechanism. This is what's called a non-local neural network. This is called non-local because unlike convolution layers, you don't have for each output node a very specific local receptive field. Instead, what you'll have is the equations on the upper right. Specifically, to compute the output yi, that is pixel I and the output y, we'll sum over all possible inputs j. And so this is very similar to a fully connected neural network, except that inside the summation, we'll have a weighted summation. That is, we'll have a weighting factor, a multiplication factor, between two functions f and g. Now, g of xj is just extracting some set of features from the input xj. The function f is a binary function that takes not just xj, but also xi, because we're computing the output at yi. And so what we're doing is we're going to compute a similarity between xj and xi, and we're going to modulate the contribution of the features from xj by that similarity. So you can see on the lower right some examples for f and g. And again, this can be generalized to many other things. These are just examples. Specifically for f of xi, xj, what we'll have is just a Gaussian around the similarity. In this case, just a dot product. A dot product is just an unnormalized cosine similarity. And so what we're doing is we're saying how similar are xi and xj, and then we're exponentiating it. And so high values mean that xi and xj are very similar, and low values will mean that they're not that similar. And so the function g of xj, which is just extracting features, again, in just a linear way, you just have a wg times xj, will be modulated by the similarity function. And so again, the output yi is just the weighted summation across all j's, and the weighting is dynamically computed based on the data. That is, you're computing the similarity function f of xi, xj dynamically. And so you might wonder, why is this different from a fully connected layer? And the fact that you're doing this dynamically is the key part that makes it different. Because when you're doing a fully connected layer, the weights are not dynamic. That is, you learn the weights and then you apply those weights regardless of the input. They're not data dependent. In this case, the similarity function, f of xi, xj, is data dependent. And so you're modulating the inputs in a data dependent manner. And this makes all the difference. It allows the network to, in effect, learn the connectivity pattern, learn for each piece of data what is important, and then sum up the contribution across those pieces of data in order to form the output representation. Here's an example from the paper showing what was learned. This shows arrows across not just space, but also time. One of the interesting things is this summation across J can be not just for the current input, but it can also be input across time. And so what we can see is that the arrows with high weights are visualized, whereas all of the connectivity that is ignored is not shown here. And so the red arrows represents high similarity function. And what you'll see is if you want to, for example, take a video which consists of many different frames and you want to extract what activity is being performed in the video, such as playing soccer or kicking, then you allow the neural network to automatically figure out which pixels to pull from across space and time in order to combine those features into an overall representation that at the end you can use to classify. Again, this shows the power of attention-based mechanisms to automatically and dynamically, in a data-dependent way, figure out what's important in the input. And it can do this in a way that's not specific to how many there are. If you notice, this function does not actually depend on anything about how many of xj's we choose from. And so if you learn this particular neural network, non-local neural network, you can actually apply it to all sorts of other, for example, image sizes and so on. And again, this is the power of these attention mechanisms in representing relationships between different types of things. And we can apply the same type of ideas for representing the relationships between words in a piece of text or between different nodes in a large graph.